Good evening. Welcome to Gates Planetarium, Denver Museum of Nature and Science. I'm David Grinspoon, the curator of astrobiology here in the Space Sciences Department. And this is a great crowd. This is just about the largest crowd I've seen for 60 minutes in space. So we'll hopefully it'll be a good one. We'll try to keep it fun-filled and action-packed. And for those of you that haven't been here before, this is our monthly program where the space scientists here at the museum sort of present stories of recent new science. One of the great things about science and space in particular is that there's always something new. The pace of discovery is amazing. So this is our chance to sort of give you real time or very, very recent science presentations. Out of curiosity, how many of you are first timers who've not been to 60 Minutes in Space before? Wow, good showing. It seems like maybe there's a large group of you that came from, yeah, who are you guys? The best meetup group in town. All right. Well, welcome. Thanks for Denver Friendship Club? Friendship One. All right. Well, thank you for coming, Denver Friendship One. And tonight, we usually have a combination of 2 or 3 of the different space scientists here at the museum presenting every month. And it's always the last Wednesday of the month, by the way. And tonight we have Dr. Dimitri Klebe and myself, David Grinspoon, presenting stories. And Dimitri will go first, so I'm going to now hand it off to him.
Thank you, David. So this, for those of you who have been here, know that I like to cover kind of deep space stories or things that are involving telescopes and instrumentation, because that's where my background is, in particular infrared astronomy, though I'm not talking about infrared astronomy tonight. But my first story, I've got a couple of them, where I'm going to try to explain some fairly difficult concepts to you today and see how well I can do at it, because I find them very interesting, and it's to me illuminates some cool things about nature. So my first story, and I've talked about this particular telescope before, it's a new one called the Atacama Large Millimeter Array. This is just as an artist's conception of that telescope array. It is still in the process of getting completed. It won't be totally completed until 2013. But it's located down in Chile, in the Atacama Desert, on the Shanantor Plateau. This plateau where the telescopes are actually, this is sunrise here, but the telescopes are way out over here in front of this mound over here, but actually right in here. And that plateau is 16,000 feet above above sea level. And the reason they've chosen this site, it's extremely dry. It gets almost zero precipitation, though in this last year they've seen some snow and things like that, which is a bit unusual for this area. And these peaks that come up around it are about 20,000 feet. But they've built this Atacama Large Millimeter Array that is going to be is really the first of its kind to look in what we call the millimeter part of the spectrum. And the reason this site is good is it's very dry, very little water vapor above the site. There ultimately is going to be about 66 antennas at this site. I'm going to explain a little bit how radio telescopes like this actually work, what the process of interferometry is. But they have the ability, because they have lots of dishes spread out, to be able to see very small or very fine angular detail onto the sky. And this particular one, which is working in the millimeter part of the spectrum, you see the spectrum down here. The visible is where we actually see with our eyes. ALMA's working out here, and by millimeter we mean millimeter wavelengths of light. So it's kind of between the infrared here and what we call the radio part of the spectrum. This kind of telescope works very much like the radio telescopes that you see. in terms of capabilities, it's going to be about 500 to 10,000 times faster than our existing capabilities in this wavelength region, and it will produce images that are 50 times sharper than what we can do until now, and it includes images with detail better than the Hubble Space Telescope. Its primary science drivers are to look at the earliest galaxies in the universe, and I'll touch on that on my second story as well, and then the formation of new stars and planetary systems. Now, it basically looks at what we call the cold universe. And when I say cold universe, I'm talking about things that are just on the order of tens of degrees above absolute zero. I always remember Celsius better, but it had to be about minus 250 degrees Celsius. So those things that are very, very cold emit in this part of the spectrum, so you can see them. So they're good at looking at, like I said, early galaxies and as well as star formation and planetary systems. A few months back, they had released this image, which I showed at an early 60 Minutes in Space, where they were just showing its capabilities. It wasn't really a scientifically based image, but they only had a few of the dishes in operation, but they're always showing some of its capabilities. This is the antenna galaxy. There are two galaxies that are colliding here, and here's a blow up of it here, and it's the image that's in this millimeter part of the spectrum are these gaseous wispy tails that you see here, and in these regions these things are glowing actually in orange, and it's overlaid over the Hubble Space Telescope image of this colliding galaxy. And this is just to point out what it's seeing that's different from the Hubble Space Telescope. In this colliding galaxy, these blue stars that you see are from the Hubble image that are new stars that are forming that you can see. Then there's these black structures that are in the Hubble image that you can see overlaid on that are all of these emissions from the millimeter part of the spectrum. They're showing that there are intense star formation that's occurring in this particular colliding galaxy. Again, these gases and dust that you see in these parts of the galaxy are very, very cool. Okay, and I'm going to show you the new result that was actually issued this week, but first I wanted to kind of explain how interferometry worked. So you have an array of telescopes. This is an image of about 19 of them. They're up over a little bit over 20. They plan, like I said, to get all 66 in operation in 2013. And so this is one of the most recent pictures that they have of the majority of the dishes that they have. And in explaining how these telescopes work, let's first look at how a regular telescope works. We've got a little red star. It's emitting light into the telescope. The telescope's job is to focus that light. It comes to a focus, which is what we call the focal plane, and then in the case of looking through a telescope, it goes back out of focus and then to an eyepiece, which you see. Now, if you're looking at a blue star that's a little bit off of an angle, there you'll see that it comes to a focus in a little bit different location at the focal plane. And it again actually comes out at a much larger angle. You'll notice when you look through telescopes, it magnifies things. This illustrates how it actually magnifies the angle at which you actually look at things. Now, looking at this image here, as I mentioned, this is actually where astronomers work. They work actually at the focal plane and is where they would put what we call our CCD detectors. In the old days, we used to use photographic film. CCD detectors are an array of pixels, 1,000 by 1,000, 4,000 by 4,000. They keep getting bigger and bigger. That's what is meant by a megapixel camera. And now we have, 10 megapixel cameras in our standard cameras. And that's where things are actually imaged. So you'll see that the red star was imaged here, and the blue star is imaged here. So this is how we typically look at a telescope. And, one of the properties of light is that it's a particle called a photon. So this is always kind of easy to picture light as photons coming in along these rays, and they're focused to this particular point. The CCD actually picks up individual photons, turns them into electrons, which we then actually sense in a circuit there. But how does the radio telescopes work? Well, first of all, radio telescopes rely more on the properties of light being a wave. And by a wave, just like a water wave, if you throw a pebble into a pond, it puts out these ripples here and they're moving out. Light behaves in that same manner. Instead of a water wave where you have water that's bobbing up and down here, light is an electromagnetic wave, meaning that the electric field and the magnetic field are basically bobbing up and down at different points in space. So when you think of it as a wave, encounters the telescope, it's a different ball game. Basically, you have your wave crests or wave troughs that are impinging on your telescope, and your telescope can be viewed as kind of like a breakwater where you have this little hole as the aperture of the telescope. And what happens when a wave hits a hole like that? Well, it diffracts around that, and your light actually starts to become, in this case, the little circular wavelets that come out. Well, what that does in terms of looking through a telescope is that you cannot focus those little photons of light exactly at a pinpoint position at your focal plane. The wave-like characters of light basically cause the image to look like this there, where you have a central peak in brightness of the image, and you have these little lobes that go off to the side. And, the idea, and we call that the diffraction limit of the telescope. That is the smallest angle that particular telescope can look at. If you have a couple objects that are separated enough, you can resolve that there's, say, two objects there, like, say, binary stars or so. If they're within that diffraction limit, they look like one kind of lump, and you cannot tell one object from the other. Well, that diffraction limit actually depends on the wavelength of light that you're looking at and the diameter of the telescope that you're using. So the name of the game is, if you want better resolution, either go to shorter wavelengths of light with some size aperture, or get a larger aperture. Well, if you're going to observe in the radio part of the spectrum, or this millimeter part of the spectrum like this story's about, you need larger and larger telescopes. And to get decent diffraction limit, in other words, good angular resolution on the sky. So when you do that, which is what the ALMA array does, it has a series of telescopes. You essentially mimic a telescope that is as large as the separation between the two telescopes. So in the case of ALMA, they can spread those telescopes out so they're like 16 kilometers apart, and that allows them to get this resolution that's like 10 times better than the Hubble Space Telescope, even though they're looking at wavelengths of light that are substantially longer than the Hubble Space Telescope. Well, how do you combine the light, though, that you receive at one antenna versus another antenna? Well, in the visible part of the spectrum, you really have no other choice, and this is just a little not a picture, but an illustration of the very large telescope the Europeans run down in South America as well, in Chile. What you have to do, and they actually combine the 4 large 8-meter telescopes and these 3 smaller outrigging telescopes, but they have to pipe the light down into a central area and actually combine that light at that point. And the tolerances are incredible. They have to be able to know the path lengths that the light is traveling down to within fractions of the wavelength of light. And for visible, that is a very, very difficult thing. But they're already putting out some pretty good results from this particular interferometric array. In the radio part of this telescope, it's actually a little easier. In the radio part of the telescope, and they're illustrating some other concepts here, but where they've masked off a couple of rays that are shorter and then longer here. But basically, when you look at things with a radio telescope, you get the information about the wavelength of the light, its phase. You can see the thing bobbing up, the electric field bobbing up and down. And you measure that and you record that. And you can record it at the different sites. And so in the radio telescope business, you basically are recording the data that's coming into the individual telescopes then goes through this correlator unit and is basically mixing those signals together and interfering them with one another. And from that, one can actually reconstruct an image on the sky. Now, if you only had 2 arrays, you don't get much of an image there. You can't really tell that much. You can tell kind of the angular size of objects. But if you have enough arrays, you can fill what they call the UV plane, and you can make what is akin to an image. And I will show you, that earlier one of the antenna galaxy was an image, and the other one I'll show you is also an image. The things that you have to keep in mind is, if in this case you're looking off in this particular direction, notice the light. These are like the rays I had showed before, light coming from some distant source. That light is arriving arriving at this antenna a little later than that one there. And so one is not only measuring these waves, electric fields bobbing up and down, you're measuring exactly at what time you're recording them. So you have all these clocks that you then have to maintain, and then you mix signals from all the various antennas, and they have the most sophisticated correlator set of computers of any kind of radio type telescope. In fact, this ALMA array pushes the boundary on all the technologies to make its measurements. And just one last point, that's basically what interferometry is, but I think it also is very cool to think about light is both a particle and a wave. So go back to our original drawing here. It's easy to see a particle kind of being bent and then focusing at a point, but that particle, even if and photons come in at one at a time, still in essence are acting like a wave, and that whole photon sees that entire aperture when it is detected at that particular point. So you can't think of the photon coming in along this red line. It is actually seeing the entire aperture. In the same sense, those radio telescopes, when we're recording the light, we're measuring the electric field, but essentially it is measuring those photons that are hitting, those radio photons, are hitting all the dishes at one time, basically. So I think that's a cool property of nature. So getting on to the observation, they turned this telescope to this particular star called Fomalhaut. It's in the constellation of Pisces Austrinus, which is the southern fish. And this telescope, being in the southern hemisphere, is looking basically at the southern sky. And I think it's a few years ago, the Hubble Space Telescope had announced, looking at the star, they had seen that there was this disk around this particular star. And this dusky disk, is seen with the Hubble Space Telescope, represents that there are very fine particles on the order of 8 to 18 microns, or millionths of a meter, size particles that are in this ring. The thing that Hubble had announced is that they had actually looked at this star a couple of times. And I should explain that to make this measurement, Hubble had what's called a coronagraph mask that blocks out the central star so that it can see the surrounding material. Otherwise, there's no way it could see this stuff out here. But what they'd actually discovered was in this little box right here, that from one time, 2004 to 2006, they saw this little planet move. And this was like the first direct image of a planet in another system. Now, at the time, they thought, or of this size of planet, and they thought it was on the order of Saturn size. But follow-on observations suggested in the infrared, in particular by the Spitzer Infrared Space Telescope, didn't show a Saturn-sized planet there. So what was up there? So they were starting to kind of doubt whether they actually detected a planet here. So just to give you an idea of this system here, where this ring is compared to our own solar system here, here's Fomalhaut B that they discovered here. Here's that ring of material. This little square here would represent all the way out to the Kuiper belt, which is out beyond Neptune. So our little Earth is way down in here, as the successive enhancements here. The distance here from Fomalhaut to this ring is about 140 astronomical units, an astronomical unit being the distance between the Earth and the Sun. So here is the image that they produced, and it's only half done. So it's overlaid on top of the Hubble image that you see below here. There is Fomalhaut B, I believe, in this image, but I'm not actually positive. They didn't point it out there. But they have now image this part of the ring here in the millimeter part of the spectrum. And you can see it's coincidence with this, but they're actually looking at something quite different. The particle sizes that they're seeing emission from here are basically about a millimeter in size, maybe a third that size. So they're much larger particles than what the Hubble actually would see here. And just to show you, so this is an extraordinary image. They've done it with only, like, I think 21 of the antennas, so it's going to only get better. Yet they're really starting to show what this particular telescope is going to be able to do in looking at nearby stars and the planetary formation. And it's turned on its side here. I should have rotated this 90 degrees, but here is that band of emission seen from that telescope. And it's overlaid not on the Hubble image, but on previous radio images of that same region. So the previous radio telescopes, this is how well they did. They got a big blob here and a big blob there. So this is doing much, much better. So we're all looking forward to the data that's going to be coming out of this telescope over the next many years, but in particular the next few years here. And the implications of what they've actually discovered here is that the ring is so tightly bound and everything like that, that their only reasonable explanation as to what is confining this ring is that it has two what we call shepherd moons, that are keeping that dust, those dust particles, in that confined ring. And they also can put some limits on the masses of those planets, and they cannot be, the outer one can be a little bit, it can be fairly small, like the size of Mars, but neither of them can be more than a few times the mass of the Earth. So that's significant in the sense that the Hubble saw that, and it explains why it was not able to pick it up in the infrared part of the spectrum. So they're now being able to, really make some inroads on defining these planetary systems here, in this case having these two relatively small shepherd moons that are moving out at distances, that are actually beyond our own Kuiper belt, where you have where we have our small icy bodies. Okay. My next story, and last story, is on this project, which announced some data of their simulations called I don't know if they pronounce it DEUCE or whatever project, but it stands for the Dark Energy Universe Simulation. It is a collaborative project, but it's mainly being directed by the French, as far as I can tell. This is just a picture of their computers, and for the computer wizards out there, this thing is equipped with 92,000 CPUs. It can perform 2 million billion operations per second in doing these simulations. So a lot of the coding of trying to figure out how to do all these parallel operations and everything. And so what are they trying to simulate? Well, nothing more than the entire universe is what they're doing. Okay, they are in this simulation. They have 550 billion particles that are utilized, that they're tracking in this simulation. And when I say the entire universe, I mean the entire visible universe. So there's few things I want to point out on this here. So, I'll go back one here. This is a slice through our entire universe. Here you show like this big sphere of the universe. As we look out in the universe, here we are, here and today, and as you get further and further out toward the edge, you go back in time. This is how we actually perceive our universe. And out here at the edge, what we define our visible universe is this region which we call the cosmic microwave background radiation. I've talked about that before, but that is the most distant objects that we can actually see in the universe. We see that part of the universe as it was 13.7 billion years ago, only 370,000 years after the Big Bang. So basically almost to the beginning of at least what we call the beginning of time in our own universe. And so there's several, and then so this here is kind of that whole image, but you can see that's an actual slice out of that. And the thing that you can kind of notice is that the structure starts to get more and more defined, and I'll show some images of what happens to the universe as we move on in here. But in this little circle right there, there is our Milky Way galaxy in terms of its size in this simulation. We are very, very small compared to the whole universe. And I don't know if you can read this timeline. I wonder if I put the wrong image in there, but it's not very clear. This is 5 billion years ago. This is 10. This is 13. And then that's 13.7. So it's not a total linear scale there. So the kind of things that they look for, and that is first that the universe, changes its character as we move forward in time. In the case of looking out here at, say, I think that was about 5 to 10 billion years ago, the universe is starting to become more and more structured. But now as you get down to our present epoch, you see a much more organized web of material here. And all of these simulations, the way they run them is they're using gravity, Einstein's equations of gravity. In this case, it's a dark matter or dark energy simulation, so they're introducing dark energy, which I'm going to tell you about, hopefully here. And but they have to start with the initial conditions, and we've measured the cosmic microwave background. That tells you how uniform the universe was to start, and so those are your starting conditions, and we see how the universe will then evolve. And we'll eventually compare these to how we actually see the universe today. Here's just a better resolution image of that slice there, and then kind of blowing up in there. You can start to see this cosmic web, and then even looking closer than that. And what they're tracing in these simulations, what you see kind of lit up here, are what we call the dark matter that makes up the universe, which we've talked about this before, but ordinary matter, which you and I are made of, only constitutes about 4% of the entire energy density of the universe. About 30% of that, or 30% of the energy density is made of dark matter, some sort of matter that has gravity, but we do not detect it optically. It doesn't interact with light. So I find these things gorgeous, and so this is what we call the cosmic web. In terms of colors, they're indicating the red areas that are a little bit more dense, and I think also are moving at higher velocities, but I may be wrong there. It might just be that these are higher density regions there. So, okay, now there'll be a test on this here later. So what are they trying to do with all of this? And I wanted to just mention a little thing about dark energy. You probably hear in the news all the time talking about the cosmological constant, Einstein's cosmological constant. The standard model for the Big Bang Theory right now is called the lambda cold dark matter model. That lambda is the Greek symbol there, and I like this thing I found on the way up here with the dark sunglasses there. And the cosmological constant really is a constant. This first equation, which is beautiful, is Einstein's field equations. The first one that he adopted when he was trying to define how the universe worked, and it includes this cosmological constant in there. And just in kind of loose terms, the various terms in here, this G actually defines how we measure angles and distances in space-time, which is 3 dimensions of space and 1 dimension of time. This R is kind of the curvature of the universe, or of space. You've heard that mass curves space, or space-time can be curved. And this T term is what we call the stress energy tensor, and that actually includes the mass and material and radiation that's in our universe there. Einstein originally included this term because at the time that he came out with these equations, he wanted the universe to be static. So gravity would pull the universe back together, and he needed basically an anti-gravity, and that's what that term did. And it is a constant term in there. And then when they found out that the universe was indeed expanding, he called that term his biggest blunder and promptly pulled it out of the equation there. And we ever since thought of it in terms of this until recently, when we found that the universe was, when we tried to measure how fast it was slowing down because of the mass in it, we found out the reverse. It was actually speeding up. It was accelerating. And the cause for that acceleration is something we call dark energy. And lo and behold, that dark energy term can be explained by reintroducing the cosmological constant in his equation. And this shows as one equation, but it's multiple equations because these are space-time. These are all the space-time coordinates there. So each of those indices are 4 coordinates there. And ultimately, if you solve those in making some assumptions, you get what they call the Friedmann equations. But what those are defining is how fast the universe is expanding at any given time and how fast it might be accelerating. So we can get all of that from these equations. And so what we're trying to get after right now in cosmology is what is the nature of this dark energy. So far, everything is consistent with this being a constant right now, but that is the kind of things that we're actually trying to figure out. So these models here, what the roles that they're going to be playing is they're going to be able to determine from one cosmological model where we have it as a constant. And I should also say when it's a constant, that means that in a given volume you have a certain amount of dark energy. So as the universe continues to expand, you have more and more dark energy, though all the energy in matter and radiation continues to be diluted because the universe is getting more and more expanded. So they're in this one, I don't want to get into the details, but these are ones that actually don't go with a constant dark energy. They have some different variations on how that dark energy comes into play. It's not constant. It varies, say, with time. So that's a couple models. So they're going to be able to differentiate between those. So they've run 3 of these big universe models with these 3 ones to try to make comparisons. And some of the comparisons that they make are things are going to be observable. So like this is just an image of the largest cluster that was formed in their universe. And this is why it's important to look at the entire universe. They can get statistics on how many clusters of this size can I find across the entire universe here. And this is just showing that structure is embedded in the rest of this particular web. So they're generating a bunch of statistics that then can be compared with the observations to see which models there are. So here's just some comparisons of those, some of the 5 biggest clusters of the different models. And, to my eye, they look pretty much the same there, but there are differences in there, and you have to do some statistics, like I said, to really differentiate one model, dark energy model, from another. And I just like this picture when I saw it on the web, and I didn't want to get into the details of this science announcement, but this is the South Pole Telescope. And it is measuring these galaxies and such on the edge of the universe as well, and is providing those observations that will play into those models. And similarly, the ALMA telescope that I told you about, because it's looking in the millimeter part of the spectrum, it actually is probing galaxies that are at the very distant edge of the universe. So it's going to be looking at structures of galaxies here. And again, these models are going to be extremely important to those observations. Okay. I am done today, but I wanted to tell you about an event we're going to have here at the museum on the 20th of May. There's going to be what's called an annular eclipse. That is where the moon covers up most of the sun, but because the moon is a little further away at that time of the eclipse, it doesn't cover up the entire sun. It leaves this little ring around there. And here in Denver, we won't have the total annular eclipse. You'll have to go to Albuquerque if you want to see that. But the eclipse starts at around 6:30. We're going to be open at p.m., so the sun is going to be kind of setting at that time. We're going to open the museum doors at 6 o'clock, and we have a variety of sun-safe activities like glasses to wear. We're going to have some solar telescopes set up, do some projection of the eclipse up on the sky terrace when we set up on the west atrium. And we're going to have a variety of things, so everybody is invited to that. So thank you.
All right, thanks, Dimitri. And I'm really glad that Dimitri gave you the equations for Einstein's theory of general relativity, because now I can assume that you all have them memorized, and I'll proceed from that basis. Let's see, what am I doing here? Well, I want to talk about something a lot closer to home in our own solar system, and back in time a little bit, involving our efforts to figure out some early history of our own solar system and the way that it bears on the early history of our own Earth. In particular, some new results that give us some new insight into the rate at which asteroids were bombarding the Earth when the Earth was young and when life was newly formed on the planet. And the way I learned about this, I actually got a call on Friday afternoon from an editor at Nature magazine. And they do this sometimes, saying she had 2 papers that they were going to be publishing in a couple of days, and could she send them to me and would I comment on them? And I said, well, okay, sure, I'll try. So she sent me these 2 papers that I'm going to talk to you about now, and I kind of read them quickly, and then she interviewed me, and I said some things that hopefully weren't too dumb and that I think will be quoted in Nature magazine when I think these are actually being published either today or maybe tomorrow. But basically, the subject is the early bombardment history of, well, in this case, the moon, but it's really the Earth-Moon system, because since the Earth and moon are so closely coupled in space, whenever there's a bombardment episode where a lot of objects strike the moon, it stands to reason there are a lot of objects striking the Earth as well, and that if we understand the impact history, the bombardment history of the moon, then we can understand the bombardment history of the Earth. And it's actually in some ways easier to study the moon, even though it's harder to get to, obviously, because the early history of the moon is preserved, because not too much has happened on the moon in the last several billion years, whereas Earth probably once looked something like this with a lot of craters, and there's still some craters on the Earth, but because Earth has such active weather and such active surface geology, the craters don't last. So actually studying the moon is one way we can learn about the early history of the Earth. So anyways, this is a map showing you all the big impact basins on the moon. Some of these, especially the left, is the near side, the side of the moon that always faces the Earth, and so some of these basins are famous and you've heard of them. And there's an interesting mystery about, I'm seeing that not all the basins are on here for some reason. Maybe, I'm not sure what this map shows, some subset of the basins. But at any rate, the point about that I want to emphasize about the lunar basins is that post-Apollo, when we've had samples from the moon and we've been able to measure their ages from different locations on the moon, we learned something interesting, that most of these big basins on the moon formed all within a fairly narrow period of early lunar history, and then they seemed to stop forming around 4 billion years ago. So this time period of really intense pummeling of the moon, and presumably of the Earth as well, is known by scientists as the late heavy bombardment. Late because it wasn't 4.5 billion years ago when the planets formed. It extended up to about 4 billion years ago. And heavy for obvious reasons, because all of these intense basins formed, and so the moon was really getting hit at this time, and so the Earth was too. And this probably had a lot to do with determining when the origin of life happened on Earth, and the environment in which the early evolution of life took place, because these impacts really drastically alter a planet when something this large hits it. So this late heavy bombardment is something that we've been really trying to understand, and understand the origin of, and the sort of extent, the level of pummeling and the extent in time, how late it lasted. And these two papers that just came out are different approaches that both bear on that question and lead us to some new insights. This is about the Archean era, which is what we call the era on Earth history between about 3.8 and about 2.5 billion years ago. So not quite as old as that late heavy bombardment I was talking about, which is right before this, up to about 4 billion years ago. So this is really about the impacts that happened after what we usually think of as the late heavy bombardment. And the punchline of these two papers, they both suggest that the rate of major impacts during this Archean era was much higher than previously thought. That in fact, this bombardment may have gone on a lot longer than we thought. And that in fact, a lot of impacts occurred on the Earth during this era, big ones, the largest of which may have rivaled the giant basin-forming impacts of the Moon, and therefore really had major environmental effects on the Earth. And these two results that I mentioned that were just published in Nature, I think today or maybe tomorrow, are complementary in that one of them is an observation of early Earth, and one of them is modeling of the early solar system. And the observation is I'll talk in more detail about both of these, but basically these layers of impact spherules, that is little layers deep in the Earth in a geologic strata that corresponds to this time period that show evidence of bombardment, because these impact spherules, they're basically the material that's formed when you have a huge impact and some rock is vaporized and then condenses and falls back down to Earth in sort of sand-shaped particles of condensed rock vapor, and makes these beds of these little round impact spherules that then we can dig up, and they tell us there was a big impact. And the other result is modeling that some planetary scientists who do sophisticated computer models of the early solar system and what was happening to the planets and asteroids. And actually this work was done up in Boulder at the Southwest Research Institute right here in Boulder, Colorado. They found that the reason to believe that there was a destabilization of a portion of the asteroid belt by a late migration of the giant planets. In other words, when the giant planets were young, they were still moving around and settling into their orbits. And as they did this, they gravitationally disturbed the asteroid belt and caused these impacts to occur on the Earth. That's sort of the punchline. Let me elaborate a little bit here. Oh, this is, I'm going to actually show you the abstracts of these two papers. Sorry, that's kind of bright, isn't it? And then I'll talk about what it means. But just to show you the actual abstract, this is the actual Nature paper, and the abstract says that impact craters are the most obvious indication of asteroid impacts, but craters on Earth are quickly obscured or destroyed by surface weathering and geology. Earth's impact history is inferred, therefore, either from estimates of the present-day rate of impacts, impact or flux, as determined by observations of near-Earth asteroids, or from the Moon's incomplete record. Asteroids hitting Earth typically vaporize a mass of target rock, similar to the mass of the impactor, and as this vapor expands in a large fireball, it cools and condenses into these molten droplets called spherules, and this is what they've been observing and modeling. For asteroids larger than about 10 kilometers in diameter, which is about the size of the asteroid, by the way, that killed the dinosaurs off 65 million years ago. For asteroids larger than that, these spherules are deposited in a global layer that you can dig up. Spherular layers preserved in the geologic record accordingly provide information about an impact, even when the crater can't be found anymore. Here we report estimates of the sizes and impact velocities of the asteroids that created the global spherular layers. And what they find is that the impact or flux, meaning the rate of impacts, the rate of things hitting the Earth, was significantly higher 3.5 billion years ago than it is now. And this is consistent with a gradual decline of the impact or flux after the late heavy bombardment. In other words, it didn't suddenly stop 4 billion years ago. It tailed off with big environmental effects on the Earth. So that's the way it actually reads in Nature magazine. Now I'll deconstruct that for you a little bit. Oh, this is, I said there were two papers. So that was one of them, which is the observation of Earth history. This is the one that's the modeling of the early evolution of the planets and asteroids. And by the way, this group of scientists, Bill Bodke and Dave Nasvorny and several of these people, Hal Levison, are up at the Southwest Research Institute in Boulder, where I worked before I came here to the museum. So these are a lot of my old friends and colleagues up there who just published this paper in Nature. But they're talking about the same thing. The barrage of comets and asteroids that produced the lunar basins has frequently been called the late heavy bombardment, and many assume that it ended 3.7 to 3.8 billion years ago with the formation of the last big basin, Orientali. But the evidence for big impacts on Earth, however, extend into the Archean and the early Proterozoic eons, which is even more recent, in the form of these impact spheral beds. So that's referring to what's in this other paper. But then what these guys have done, and this is just the number of beds at different times, but here's what they've done. Here we report that the late heavy bombardment lasted much longer than previously thought, and they're modeling where the impactors came from and why, with most late impactors coming from the E belt, which is an extended and now largely extinct portion of the asteroid belt, the inner asteroid belt between 1.7 and 2.1 astronomical units from Earth, which means just outside the orbit of Mars. And this region was destabilized by late giant planet migration. And E-belt survivors now make up the high inclination Hungaria asteroids. What that means is, I'll show you some pictures, but there's a rare population of asteroids now that they think, and they have reason to believe from their models, are the remnants of the population that hammered the Earth and Moon. And now they're just talking about looking at the existing Hungaria asteroids and doing their models that produced these craters on the Earth. They also produced about 15 terrestrial basins, that is giant craters, between 2.5 and 3.7 billion years ago, as around 70 on Earth and 4 on the Moon, Chicxulub-sized. Chicxulub is the crater in Mexico that marks where the dinosaur-killing asteroid happened 65 million years ago. So they're saying 70 that size or larger hit the Earth between 1.7 and 3.7 billion years ago. So that's a lot of big impacts. Now let me unpack that a little bit for you. First of all, I want to talk about this. Looks like it says the NICE model, but it's actually the Nice model. Nice is a city in France where this model was first developed at an observatory there. And this is the standard model for the late heavy bombardment, for what caused it, which, by the way, the Nice model was developed by a lot of the same people that wrote this new paper up in Boulder with their colleagues in France. So the idea is that there was a large-scale repositioning of the giant planets that triggered a solar system-wide bombardment of asteroids and comets, which lasted 100 to 200 million years. And that is the standard model for what caused the bombardment, because we know that when the giant planets first formed, their orbits were not completely stable and they jostled around for a while, and that jostling around destabilized a lot of asteroids and sent them flying into the Earth and Moon. So that's a long time, but it's not long enough to explain these Archean spheral beds. In other words, these beds of these little glass beads that I described that have been found on Earth from a time more recent than it is believed that the late heavy bombardment ended, between 2.5 and 3.8 billion years ago. So this is a good idea and seems to work to explain the late heavy bombardment, but it doesn't last long enough to explain these spherules. So what these guys have done now is they've postulated a missing source of impactors from the inner edge of the main asteroid belt between the orbits of Mars and Jupiter. And then they've done models that back this up. So this region is now unstable. An asteroid, if you put it in this region now, it doesn't last there. It gets gravitationally perturbed. But that may not have been the case 4 billion years ago, because the giant planets which determine the stability of other orbits were in different places. They were in a more compact configuration. The giant planets were closer together. So what these guys have done is they've created a hypothetical extension to the primordial asteroid belt, and I'll show you a picture of where this is in a minute. And then they've done their very sophisticated gravitational model, and they've tracked what would have happened to the bodies in this hypothetical larger early asteroid belt. And they tracked what would happen to those bodies when the giant planets reorganized themselves. And it turns out that the bodies from this area, this would have delivered numerous big impactors to the Earth and Moon over a much longer time than the classical late heavy bombardment. And this model reproduces a tiny population of asteroids called the Hungarias, which in fact we see today. And they now think that these Hungaria asteroids are a reservoir of a relatively stable these are relatively stable but fairly small asteroids, but they think that they are the remnant of this much larger population that caused this bombardment. This is just a picture of the asteroid belt. So these are the orbit. There's the sun. There's the orbit of Mercury, Venus, Earth, and Mars. And there's the orbit of Jupiter. And the asteroid belt is this massive collection of wayward small objects orbiting between Mars and Jupiter. But this inner region here, just outside the orbit of Mars, is pretty cleared out now. But the idea is that early on it might have been very densely populated. And as the giant planets shifted around, that area might have been perturbed and sent all these objects in that went crashing in to the Earth and the Moon. Now this is real data for the asteroids today, and they're split into different families of different, so this is the distance from the sun. So this is where the sun is, this is the distance of Earth, the distance of Mars is about here, and then the inner are actually about here, and the inner edge of the asteroid belt is here, and this albedo just means brightness. So these ones that are up higher are very bright asteroids. The ones that are down lower are very dark. And these 7 objects right here are the Hungaria asteroids. So these are real objects today, and they're in very close to the inner edge. And what these researchers are surmising in this paper and backing it up with some modeling and sophisticated simulations is that these are the remnants of a very large population in this part of the asteroid belt that is no longer there because they were disturbed by this reorganization of the giant planets. These are some of their actual model results. Let me explain this graph. So they started off with a simulation of a very large population of asteroids in the inner part of the belt. Now, in this graph, this is distance from the sun. So this object here, this is the orbit of Mars, and then the asteroid belt goes out from there. And these numbers here, this is inclination. In other words, how tilted the orbits are. And the planets, like Mars, are all close to 0 because, as you know, the planets all orbit in a plane and they're very flat. But the asteroids are not all in that flat plane. Some of them have higher inclinations, meaning they have orbits that are tilted up and they extend north and south of that plane with the planets. And the Hungaria asteroids today are in this box where this is their distance from the sun, and they're also on these very tilted orbits. So what these guys did was they started with a fake asteroid belt with all of these objects, and they put it in their model and they let it evolve. So this is 0.6 billion years before, or 600 million years before the late heavy bombardment. And then this is just before the late heavy bombardment, 0.05 billion years. And then they're letting the outer solar system rearrange, and then they evolve the system for 4 billion years. And this should say after. That's a major typo for Nature magazine. I noticed that tonight when I was preparing this talk, and I was wondering if they fixed it before it actually got published. I'm afraid maybe they didn't. But 4 billion years later, after the late heavy bombardment, meaning now, what's left of this population? Well, it turns out it's all in this box. That's where the Hungaria asteroids are today, and the rest of it has been scattered and disappeared. So in other words, they start with this hypothetical population, and they run their model, and they end up with a population of these asteroids that looks very much like what we see today. So this lends support to their idea that there was this huge population of asteroids in here that's no longer there, and that was the source for the late heavy bombardment and the pummeling that occurred after it. And when they do that model, they can also model the rate at which things hit the Earth-Moon system over time. So on the bottom here, this is time. This is the late heavy bombardment peak, which was about 4 billion years, well, it says 4 billion years ago. This is before that, and this is after. And then this is the present day. And so this shows the rate of bombardments was very high up until about 4 billion years ago, and then declined steadily to the present day. And these are, I'm not going to explain the difference between these curves. They're just different model assumptions, but they all basically do the same thing. And the interesting thing is that before this work, people assumed there was a spike of bombardment that decreased very rapidly, and that then the impact rate, today's impact rate, has been pretty much the same for billions of years. So this shape would have gone like this. But this model now suggests that this time period of Earth history was a time when there were a lot of bombardments still happening. And this is also borne out by this other evidence now of the impact spirals. this actually shows a model of the size of impacts over time that you would expect given this model. I'm not going to explain this now. It's sort of similar. These are the number of impacts you would have on the moon, and these are the number of impacts you would have on the Earth at the same time. There are more impacts on Earth because Earth has what we call a larger gravitational cross-section. It's not just physically bigger, but because it has stronger gravity, it sucks in more objects from any given population. And these are basin-sized impacts, the really giant ones, and these are Chicxulub-sized impact or dinosaur extinction-sized impacts. These make 100 kilometer or 100-mile diameter craters. So these are not small, but and these are the really giant ones that are up to 1,000 kilometer diameters. And this is mapping those over time. And the other paper, this other piece of evidence, has to do with these impact spheral beds. And this is an actual picture of what these look like when you dig them up over the ground. This is known as the revelospheral layer. And these are millimeter scale circles. Each one of these is millimeter scale. And these are formerly molten droplets ejected into space when an asteroid struck the Earth. And in this case, about 2.5 billion years ago. And then they fall back in. They return to Earth and are concentrated in certain geological layers. They originally were glass and crystal, and they still contain substantial extraterrestrial material. Substances like iridium, which are very rare in the Earth's crust, but common in extraterrestrial material. So it's very well established that that is, in fact, what these are. These rock layers are millimeter to sometimes centimeter thick layers with these tiny little spherules, and they're impact debris, sand-sized droplets from plumes raised by mega impacts. And in this work, they described how at least 12 of these have been found deposited between about 3.5 and 1.7 billion years ago. So this is well after the end of the late heavy bombardment, which supposedly ended 4 to 3.8 billion years ago. So this is evidence in the surface of the Earth that this bombardment lasted a long time, and it's very consistent with the results of this modeling that's been done up in Boulder, which is why it's kind of neat that they published these two papers together in Nature, because they're very different avenues of investigation, but they are helping to create a consistent story of what was happening to our planet at this pivotal time in planetary history. And this is an artist's conception of a large impact striking Earth. And one of the reasons I think that this is such an interesting piece of work or series of works is that it really, it maybe answers some questions, starts to answer some questions about what the environment of the early Earth was like at this time. And clearly it was dominated even later in Earth history than we thought by these giant impacts from space, which scarred the moon and scarred the Earth too. It's just that those scars on Earth are mostly gone now, although if you dig in the dirt carefully enough in the right places, you find these spherules which record this. But this, maybe answers some questions, but it poses some really fascinating new questions. And the question that I'm really concerned with is, what did this do to the evolution of life on Earth? And what kind of effect did this have in the early evolution of life? And one interesting observation that's been made is that if we look at the different organisms on Earth today and you compare them biochemically, you can actually do these very sophisticated studies of what is related to what and how long ago they diverged by looking at similar proteins and how they mutated over time. And you can, from doing that, you can derive the properties of what biologists call the last universal common ancestor. And so even though we don't know what this organism was, genetically and through using molecular biology, we can derive some of its properties. And one thing that's been learned from this approach is that the last universal common ancestor, which probably lived more than 3 billion years ago, was what they call a hyperthermophile. That is, it survived in very, very hot conditions close to the boiling point of water. Now, the Earth probably wasn't that hot all the time, close to the boiling point of water, billions of years ago. We have evidence that it wasn't. But if occurrences like this happened occasionally, where when with the largest impacts, the oceans would almost boil off. They would, a lot of heat gets deposited in the environment. And so it may be that this last universal common ancestor was a hyperthermophile, because those are the organisms that survived these events that almost sterilized the entire Earth and almost boiled off the oceans. So there may have been a sort of filter where only the organisms that could survive these events that almost extinguished all life on Earth by almost boiling off the oceans, if the only organisms that survived were ones that could survive in very, very hot water, almost boiling water, then all life subsequently on Earth would be the descendants of such life. So it may be that this massive continuing bombardment when life was young on the Earth explains why our last universal common ancestor was a hyperthermophile, or an organism that could live in very, very hot water. That's speculative, but it's clearly there are connections that are yet to be uncovered between the evolution of life on Earth and this bombardment history that we're learning more about through a combination of studying the moon, studying the early Earth, and modeling what happened to the positions of the planets and asteroids in the early solar system. So that's all that I was going to report on tonight. And now I think we would like to entertain your questions if you have any, and maybe Dimitri will come back down and join me, and we'd both be happy to answer any questions you have.
Why don't you show the next slide for the next?
Oh yeah. Ta-da. Just a reminder, thank you. Just a reminder, the next date in the series will be May 30th, and probably lots of cool stuff will happen in space between now and then, and we'll tell you about it. Okay, any questions? Yes? Great question. She asked about the animals that they found around these hot smokers, black smokers they call them, in the ocean floor. These sort of chimneys where hot, very hot, mineral-rich water is pouring out of the ocean floor, and they found all these communities of organisms that live down there, mostly independent from sunlight. That's a great question, and the question was, do I think that the organisms there might be similar to these hyperthermophiles? Well, in some ways, I mean, those are modern organisms, so they're not the last universal common ancestor. But yeah, they do like hot water, and it's an interesting point, especially because it's been pointed out that if this was going on the surface of the Earth, that a safe place to live, relatively safe, might have been the bottom of the ocean. And for that reason, some people think that it's possible that very early life, before it colonized the top layers of the ocean and the land, may have actually the origin of life and early evolution may have occurred at these hydrothermal vents on the ocean floor. So yeah, I think there probably is a connection between those organisms and this last universal common ancestor, but obviously it's an indirect connection in that those are modern descendants of this very ancient organism that we're still trying to learn something about. Oh, yeah.
Related to the hypothermophiles and the various organisms found near these smoker chimney, do you think the fact that things can survive in these areas is a sign that similar organisms can be found on other planets?
Good question. So is the fact that there are organisms on these seafloor vents suggestive that that life could survive in similar environments on other planets? Yes, if there are similar environments on other planets. In fact, people have suggested that Europa, moon of Jupiter, ocean moon of Jupiter, may have something like these kind of seafloor vents at its interface between the ocean and the solid part of the rocky part of the moon underneath the ocean, because in fact we know there's tidal heat inside Europa. So yeah, there may well be similar environments some other places in the solar system, and if so, then the fact that, I mean, just in general, when we find exotic organisms on Earth living in different kinds of environments that we didn't know could be inhabited with different kinds of physical conditions, it increases our knowledge of the ability of life to live in a lot of different environments, not just the environment of the surface of the Earth that we're used to. And that, in a broad sense, makes it seem more likely that life could adapt to conditions on other planets. And specifically, if there are black smokers on a place like Europa, then yeah, it encourages us to think that there could possibly be life on such a place. Yes?
Yeah.
Back to that, the star you were showing us.
Yeah, the Fomalhaut star, yeah. Do you have the clicker? I wonder if I can go backwards fast enough.
Look at that, he's fast.
Let's get her back through all this deep space stuff. So this one here, or did you want to see the Hubble Space Telescope one?
This one. Wouldn't the size of the star and the distance from the star kind of make up for the? Couldn't that expand the kind of Goldilocks zone?
So you're asking a question about where the Goldilocks zone might be in this particular system here. So the Goldilocks zone, for those of you who don't know, is that area where a planet can exist around a parent star where you can have liquid water on the surface there. So this star isn't what we call an A star, which is a star that's a little brighter than our sun. Well, actually quite a bit brighter than our sun, but its Goldilocks zone would be further than the Earth, but it'd still be on the order of a few astronomical units from the star. So this particular region out here in this disk here is 140 times the Earth-Sun distance. So this is in a pretty cold part of space. So it is pretty akin to the Kuiper Belt, which is where our icy bodies are, which Pluto is a Kuiper Belt object and everything. So I don't know the exact distance from that star, but it'd be substantially closer in than for these planets that have been discovered out here. So even though this inner one is now thought to be on the order of a few times the mass of the Earth, it's extremely cold out there. Other question? Way back there.
Yeah, what's the status on opportunity?
Do you have a status report on opportunity?
It's a really good question. If Steve Lee were here, he could give you the exact answer to that. But last I heard, opportunity was still observing around the rim of Endeavour Crater and this area called Greeley Haven, that they named after Ron Greeley, the planetary geologist who passed away recently, who was important in Mars exploration. And I think that the status is positive. It's operating well. You know, a few glitches here and there, but I haven't heard any dramatic recent news. So as far as I know, its opportunity is still the sort of miracle rover, still surviving way after its projected expiration date. And maybe, hopefully, for the May 60 Minutes in Space, Steve will be here and give us the detailed update. And then, of course, in August, if all goes well, there'll be a new rover in town on Mars, Curiosity, in the front row.
Dimitri, back to Omaha. Are there other methods that could help confirm these planets, like the radial velocity method, or are these orbits too big for that?
So the question is, are there other methods to actually confirm that there are planets that are here in those particular locations, or yeah.
These are kind of fuzzy little dots in a picture.
Yeah, well, so Yeah, the emission that you see in this dust ring right here, taken by the Hubble, is we're talking really small grains of dust. So there's no planets there. So the only planet that's been discovered was this particular object right there. So and they saw this move, in this 2-year period, and consistent with moving around Fomalhaut. So like this is a background star over here. This was the first. I don't know all the qualifications on it, but it really was the first direct detection of a planet. And there were a few other ones that had followed in the same line here, where they had put on a coronagraph mask and everything. So it's going to be a while before we make many more direct planet finds, just because we need fairly large telescopes to do that. And one of the things of all the surveys that we're doing, where we're going to now be turning into closer stars, is that when we find, say, a transiting planet there, it's close enough that we can train big telescopes to try to image those planets. So the ALMA array, what it does is it's imaging the cold gas and dust that's basically around these star forming regions. So I'm interested in when they start going to other disks here, what they're going to find, because these are beautiful results. And then, like I said, they're a half the, or 1/4 of the amount of antennas I think they utilize to get those images that you saw, or that image that you saw.
Yeah, I have a question concerning if we have those two studies that conclude the heavy bombardment period happening potentially later on in Earth's history. I don't know off the top of my head the time period of the Earth and Moon potential collision. What are the implications of how that would affect the Earth-Moon collision? And
Yeah, the question is, given these new results about the bombardment, are there implications for our understanding of the moon forming, the giant collision into Earth that formed the moon originally? And that event was even much earlier. That, as far as we understand it, and we have some pretty good data that supports this, the origin of the moon was very, very early on, less than 100 million years, probably just if anything, a couple of tens of millions of years after the Earth formed. So that was the Earth and Moon formed almost simultaneously. So even the 4 billion year old late heaven bombardment is still well after the origin of the moon. So I mean, it's all part of this, trying to puzzle out this same story, but there's no direct bearing on the origin of the moon, because that was even earlier than the period of time that we're talking about. Other questions? Over there. Uh-huh. Oh, the Tunguska incident. Yeah, event. Yeah, he's the gentleman's asking about the Tunguska impact, which was an event in, I guess, Siberia, Tunguska, in the former Soviet Union, that was was it 1908? That sounds right? Yeah, and it was a huge explosion, and it flattened trees for hundreds of miles. It was, fortunately, it was in this very remote area that was mostly forest, but it was the pressure wave was sensed as far away as England. And the strange thing about Tunguska is it didn't make a crater on the ground. There was a huge blast wave, but no crater, and very few remnants of the object itself. And what is believed now by scientists about the Tunguska event was that it was a comet, a small comet, and that it exploded in the air. It was an airburst. And actually, if you model the forces on a comet as it's coming in, it's very hot, it's vaporized, it's icy on the inside, and they're not really strong objects. They're sort of loosely bound snowballs, and as that stuff starts to vaporize and as the forces increase as it comes through the atmosphere, you actually can get them to basically explode from those forces. So the Tunguska, as far as we understand it, that event was probably a small comet that came in and basically exploded before it hit the ground, and it was that explosion that led to all those blast effects that were observed. So
I just had read something pretty interesting recently on that event there, and the trees that were right below that basically were still standing with their branches just totally, strafed off. So that was pretty interesting.
because the forces
The forces came directly down.
Wow. And I think you can still, there's still forests there where the trees are basically rotting, but they're still kind of all lying down the way they were at that time.
Yeah, question here.
The Webb Space Telescope, is that an interferometer?
The Webb Space Telescope, is that an interferometer? No, it is not, actually. So its main thing that it's going to be doing related to the talk that I gave here tonight is that it's going to be looking at little longer wavelengths than the Hubble Space Telescope. They often talk about it being a replacement for the Hubble, but it's a follow-on, but it's going to be exploring the infrared part of the spectrum, but with a larger mirror so it can get good resolution. It's going to be looking at those early galaxies in that, 13 billion years ago. The first galaxies were thought to form in the order of 4 to 800 million years after the Big Bang, and that's going to be one of the main things that James Webb will be actually looking at. But it's your regular type telescope. And that means that it's got a bunch of mirrors there that have to deploy. It's an interferometer in the sense that it's an optical one where those mirrors have to be positioned such they assume a shape of some exact profile, some parabola or hyperbola that is aligned within fractions of the wavelengths that they're going to look at. So in the infrared part of the spectrum, it is a little easier to do than to try to do it, say, in the optical there.
But this time, unlike the Hubble, we're going to get it right the first time.
Yeah, we have to.
Because we can't go up and fix it, actually.
Yeah.
This is a comment for Dave. I read something in the paper about your recent being recognized as a chair of some department in Washington or something.
Oh yeah, thanks for asking. I wasn't going to talk about that tonight, but I will. Maybe at one of these 60 Minutes in Space, I'll give a little presentation about what I'm going to do. But there was a little note in the paper that I recently was selected for kind of an unusual honor, which is that I applied for and was chosen to be. I'm going to be the first ever Library of Congress Chair of Astrobiology, which means that in November I'm going to Washington for a year. I'm going to take a year-long leave of absence from the museum, and I'm going to go to the Library of Congress and study and write a book about astrobiology and society, and then hopefully finish it up and publish it and come back here and get back to work. So that's an honor that I've recently received, and I won't start talking now about the book I'm going to write because that would be another hour, and then it'd be 120 minutes in space. But thanks for asking, and I will be giving some kind of a presentation about that coming up. Yeah. Thank you very much. Yeah. Yeah. Thanks a lot. Does anybody have a last question or two before we wrap it up here, or should we call it a night? Oh, yes. I'll hand that one to you.
I suppose they'll be working on it. If there's money in it, then we'll definitely have it.
Pretty soon Google will own the universe.
Yeah.
Google is the universe.
Maybe a last question over here.
Yeah.
With the Deus project, the one with the simulated universe, with the ability to look backward in time, do they expect that to help them extrapolate perhaps predictions about how the universe will evolve in the future?
Yeah, so you can use that same model to keep evolving forward in those models. It turns out that a lot of the, stuff happened early on there. So if you were to evolve further on in the future, you'd have to probably go out to about 30 billion years before you had some significant change to what we see today and everything. It's an interesting question because one of the predictions of the dark energy is not very good for our future universe. Basically, as the universe continues to expand, the mass and the radiation get diluted there because there's only a certain amount of it there. But the dark energy, if it indeed follows this cosmological constant, continues to increase and increase. And that continues to accelerate the universe. And one of the strange things that happens is the things that we see today eventually start to accelerate over our horizon. So there is a time, and I think it's more like 100 billion years or even 1 trillion years out into the future, where even the cosmic microwave background radiation, which we've learned so much from, is not observable anymore. And which, begs the question that astronomers living in this universe 1 trillion years ago will not be able to figure out where they're at.
Well, I'm not going to sleep tonight.
Yeah. All right, thank you. Yeah.